Okay, so I'm aware that in the last few videos we've kind of been doing a lot of, for lack of a better way of saying it, really deep math that can seem somewhat confusing. I mean, we had series, and then some of them were geometric, and then we cared about their convergence or divergence. Once we had their convergence, we found an interval of convergence and a radius of convergence, and we had different centers for the different intervals. And then we said last time somehow we were going to find a function, or given a function, find a geometric series representation for it, and then we could use that to approximate the value of a function. And somehow there were also apparently derivatives and integrals going on with that. And I'm aware that all of that kind of thrown together can seem somewhat convoluted. So I figured I would do this really quickly just to give you an idea of what's going on. Suppose we have this series right here, x to the n over n factorial. And without doing lots of convoluted math, it should be obvious. That's exponential for any x. That's factorial. Factorial is going to go bigger than any exponential. So ultimately, this whole thing is going to go to 0, and it's going to converge. And more to the point, if we actually did the test for the radius and interval of convergence, we actually did it in an earlier video, it's going to converge everywhere. But now, actually write the terms of that series out. If we did, at 0, we get x to the 0, which is 1, over 0 factorial, which is also 1, plus, at 1, I get x to the 1, which is x, over 1 factorial, which is 1, plus, at 2, I get x squared, all over 2 factorial, which is 2, plus, at 3, I get x cubed, over 3 factorial, which is 6, then I'm going to get x to the 4th over 4 factorial, which is 24, and I'm going to stop right there. But we have a nice simple pattern there. And then last time, we said, well, if I have a series, it's kind of like a polynomial, and one of the reasons we use these series is because derivatives and integrals are actually really easy because they're essentially polynomial in nature. So take the derivative of that. If this is the series right there, just call it f of x equals that series. Find f prime of x. Well, I can just go term by term. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2. Bring down the 2. It cancels with the 2, and you're left with an x. This term, bring down the 3, so you'll be left with an x squared on top. The 3 will cancel with the 6 and leave a 2 on bottom. Here, bring down the 4, you'll be left with an x cubed on top. 4 over 24 will leave you with the 6 on bottom, and so on and so forth. And now, what do we see? Well, this was my original series. This is derivative. This is its derivative. And what do we immediately see? Well, this series has itself as its own derivative. And again, I've mentioned this before in these videos. This is where in class I would pause and I would wait for you to stare at it and see how incredibly amazing and cool and awesome that is, and then say, and what does that mean? Well, that's a function. That's its derivative. And it's a function whose derivative is itself. Do we know any functions whose derivatives are themselves? Well, yeah, actually. If f of x equals e to the x, we know f prime of x equals e to the x. But if this series has itself as its derivative, and these series are functions that are used to represent other functions, well, then it seems pretty clear that if I wanted, I should be able to write e to the x as the series n equals 0 to infinity of x to the n over n factorial. And now, well, so far, the only functions we have found series representations for were nice fractional type ones that we could easily write as geometric series. This one you clearly can't. It's really messed up. So there's a few more tricks that we need. Another really big major theorem we're going to need. But once we go through that theorem, we'll then be able to show that this is true. We can see it right here just looking at the first few terms, but we'll be able to show that this is true right here. That e to the x can be represented by this power series right there. But clearly, if I differentiate this, I can also integrate it. And now your brain should start to say, wait a minute, does that mean if I wanted to integrate some function, maybe e to the negative x squared? I think several of you mentioned that in your physics class, Mr. Brickman mentioned this function right here and said you couldn't integrate it, which is true. You can't integrate that. But if I can take this function and make it look like that function, there's pretty much a direct substitution. Replace x with negative x squared. Then I can find the series representation. I can use the same one. Replace x with negative x squared. And now we are not there yet. This is going to require more work. But that means now, at least for right now, I can guess that this function has a series representation right here. And then if I want to integrate this function which can't be integrated, maybe I can integrate the series. That's just polynomial in nature when I actually expand it out. And I know I can integrate that term by term. So ultimately, this is the goal. Don't lose the forest for the trees with all the math that we did in the last few videos with trying to generate these power series and all the algebraic manipulation. This is still the goal. Given a function that can't be integrated, find a way to integrate it. And it actually is pretty clear right here that, well, this trick should work right here. Good. Have fun. Explore. Do math.